Any students? So just to notice who's here at the moment: Wafia, Sarah, Sahar, Nino, John Ruben, Hassan, Ern, Abdul Hadi, and Eliazuri, Rawan, and Ashraf. So I guess a lot of people didn't want to come into class today. That's okay. Now, last lesson, we actually looked at this stuff here at the abstractions thing. So I'm not going to go through that again. Now, actually, I'm having a bit of a trick getting it to center on the page so that you can see it. Let's put that away. Yeah, there. So we talked about this. So I'm just a sort of a reminder of this. Do you remember this from last lesson? We talked about abstractions, correct? You guys remember? And in particular, we talked about these ideas of layering of abstractions. If I was going to summarize that discussion, it would be that when we're abstracting, we're removing information from what we have. And we're removing all the information which is irrelevant to our solution of the problem. And so as we go to solve the problem, we have a lot of details that represent the current state. And some of those details we remove out to get something which is easier to work with. And we talked about layering, which I'm showing you here. That's just, again, this is a review of what we looked at. But do you remember the turnstile thing, where we can have a model where actual states are recorded in the model and changes of states are recorded in the model. This is quite important in computing, because in computing we do that, things change. Now, this model was about a turnstile, which allows you access onto the metro, and you have to pay to get access. So you pay at the turnstile, and then the turnstile unlocks. And then you go through the turnstile and it locks again. So you have two different states, the locked and the open state, and they are changed by these actions that you can take, which cause a transition from one state to another. And so when you insert a coin, that's an action, and it causes a transition from the locked to the open state. When you push, that's an action, and that causes a transition from the open to the locked state. And so we have these states, and we have these actions. Now, do you remember this model here? So that was a dynamic model, because things change, states change. In a city, things change very slowly. The problem with this is a model, it's a map. A map is a model, but it has so much detail. It'd be useful for you if you wanted to find a house in there or something. But for somebody who wants to solve the problem that Leonard Eulen wanted to solve, which was how many, is it possible to go across all the bridges in that city without going across the same bridge twice? This model is not very helpful. So we abstracted it a lot, or he abstracted a lot to get this other model. And lastly, there was this concept of data modeling, which you will get into in your courses later in your degree. Because yeah, you have to have some way of referring to the data that you have. Now, did we go through this? You tell me. I think we went through this also. You tell me if we didn't, because I just want to make sure that we've covered everything that we need to go through in the course. Now, bear with me on my, you might say, well, yeah, he's old, all right. And so he can't even remember what I taught, because I have 2 classes, right? And so, yeah, we covered this, right? Remember the fetch, decode, you remember these models? Yes, that's all been done. So that's just a little bit of a reference for you as well. The idea of an algorithm being the last point there, that is our way of sort of representing things in a recipe type way that can be run through a computer architecture. There was a drawing of computer architecture there, which is quite complicated, but the only reason why that was is to sort of get you to see the small components there, which were involved in the fetch, decode, execute cycle. So we've done that. And so there's one last thing here to cover, which is this last set of slides that I'll try and go through with you now, if you don't mind. Just it should take just a minute. It's not a lot of detail here. So with the fetch, decode, execute, we can apply algorithms to them. Algorithms are kind of like recipes. So for example, if you had a recipe, you might think of something like this. What are you making here with espresso powder? My gosh, you know that. So that's a weird one. It's making a cake. All right, so it's going to be a coffee cake, I suppose. But what we have is we have some ingredients, which I suppose you could consider to be like inputs. And then we have some instructions, which I suppose you could consider to be like processes. And then you will get an output at the end, which will be a cake. So this term, algorithm, what it's about, and I got a couple of things in chat. People just saying hello, that's nice. These things that you're going to get, the algorithm is step by step, would cover that recipe. You'd say, you know, of all the processes that you would do in that recipe, and also would mention the inputs and the outputs. Now, in this little list here are 3 different ways that we can actually represent an algorithm. So we can just write an algorithm down in words. So you could say that this recipe here, the instructions in particular, represent an algorithm. So that's an algorithm. It's step-by-step instructions to do something to get an output. Pseudocode is like English. Some people call it structured English. And so the structured part of that term is quite important, because pseudocode, is the idea when we write pseudocode, it's taking our recipe, but keeping in mind how the computer works, you know, with our fetch, decode, execute, keeping in mind how that works to write our English in such a way that it's easy to translate it into a computer language. So that's pseudocode. So some people refer to that as structured English. And we have other tools, one of which is a flow chart. There's other charts that we could use, but flow charts are particularly useful because they have processes and they incorporate the concepts of 3rd-generation programming languages, which are sequence. I don't know if you've heard of these things, like sequence, which basically means that one instruction comes after another instruction, and whichever instruction is first in line is executed first. You know, that's sequence. Then we have branching, which means that we can come to a point in our code where we can choose to execute a branch of code or not, or execute a different branch of code. So that turns up in computer programs as if statements or loop statements or do while statements. All of these things can be incorporated into a flowchart. Now, I mentioned that flowcharts incorporate, as I was saying, right, sequence, step by step, branching, and related to branching is a thing called iteration, which means that we can repeat things over and over again. You need to do branching to do iteration, but all of those things can be shown in a flowchart. Now, this is a somewhat trivial example of somebody applying the wrong algorithm to the problem because they didn't understand the problem. So the gentleman came along and he found a sword in a rock, and so he assumed that that this was Arthur's. I don't know if you know the story about Excalibur. You know, yeah. Excalibur is sort of magic, all right, you know, from the medieval times, right? There was, and the magic, a wizard put some magic in this sword, and whoever had the sword would be the king. And so this person misinterpreted that, and so pulled on the sword, and the sword. So he didn't really understand the algorithm, and he ends up stuck to the rock. That's kind of a morbid story. Anyways, so there's the story. It's different than what we might have normally thought. Here's an example of a very, very simple flowchart. And I mentioned a minute ago that flowcharts can include iteration and branching. This one doesn't. This one just has sequence, but sequence is nice. All right, so sequence, what we've got in here is we've got some connectors. We call these things with rounded edges connectors, and they can be endpoints, terminators, and connectors, really. They can be endpoints, start points, but they could also be, because sometimes our flowcharts are so big they won't fit on one page. So we'll put one of those down the bottom of the page and say, go to the next one. And on the next page, we'll have one to start it off with. So we have those connectors. Then we have a bunch of statements. And you see that the statements are represented by these rhombus type shapes and a rectangle shape. So this is where our processing is going. Now, on the right side of that, we have the same recipe, if you want to call it that, or the same algorithm is represented in pseudocode. So I told you pseudocode is structured English. And so here in our pseudocode, we have a begin and an end, same like that. And then we just have our statements in order. The sequence is important, just as it is here. In this flowchart, it's implied in these lines, these connecting lines, that they're one directional. That is that where all of these could be represented by arrows going down. Okay, so once we've got our pseudocode or our flowchart, we can implement it in a program. And our computer programs, this is ideal for a third generation programming language. We'll have a look at them in a second. But our computer programming languages, basically what they are is they have an interface where we can communicate with them in something that looks kind of like English, but not so much that, something that we can understand, and then that's translated, interpreted, or compiled by the computer to change it into zeros and one code, which the computer can understand. So this is what the computer understands, this stuff here. This is the stuff on the top left. That is computer. Can the people at home see this? Where my arrow is? Yeah, okay. Yeah, you can, so that's good. So this stuff on the top left, that's what computer understands. So that's the only thing that computer understands. So what we actually have is, to make it easier for us as programmers, we have layers that sort of sit above that. And so we can use hexadecimal instructions like this. This number here is a hexadecimal number, 2004, which is going to sort of refer to this location, and that location has this instruction in it. So that's how that's going to work. We can use Symbolic Unicode, which is then, so that's going to be things like this. LDA 004, which means load the first operand into AC. Well, AC is a location address in the memory. And so you have to be pretty sort of good memory and very precise and accurate to sort of write computer programs like that. But this would be how computer programs were written before we got our second and third generation programming languages. Assembly language is a step above that. And every time we go a step up, what we end up with is something that's easier for people to work with. And so assembly language is going to do something like org-o, which means the start of the program is location 0. Then we're going to do LDA-A, which, and I hope you can see that there's a mapping between this instruction and that instruction. Basically, we've taken these very symbolic, simple codes, and we've just made them something that's easier for us as a human being to sort of relate to. Up until the 1950s, that's what you had for computer programming. You'd have to write computer programs like that. Since the 1950s, we've got a bunch of computer languages that have been developed for us, Fortran, C, Java, etc. And you'll notice that we are able to write programs now that look like mathematical statements and look like sort of English statements. COBOL was really classic in that. I mean, we use big words in COBOL. And when I say big words, I don't mean those words that people don't understand, but I mean things like ADD, add, so you can do things like that. And big names for variables. So machine code was the first one that we were talking about. This is the machine code here, the binary program. That's the computer still uses that. But what we've done is above that, layers above that, we have ways of sort of translating what we want to say into that machine code. And so the operating system is part of that, but also we have sitting over that our other languages. Assembly is a second generation language. So machine code you could call first generation language. We say native, meaning that's the language that the computer understands. Assembly language or assembler is this one here. What we've done is we've taken something which can be easily understood. We've translated it through a couple of phases to get something which still is fairly cryptic, but at least human beings can work with it a little bit better. Then we get to our higher level languages. Oh, by the way, there's a point there that I should make out. They are CPU specific. What that means is they're CPU specific because they actually refer to address locations for registers in the computer CPU, and they will be different depending on what CPU you're using. And so you'll have, a program that you wrote in assembly to run on your one computer would have to be changed to run on a different. Nowadays, we have operating systems that take care of that for us. So our high level languages, that's where we're getting into things that you might come familiar with. You may have seen Python. You may have seen the C programming language. You may have seen Java. These are our higher level languages. They're portable. That means that you can take them to different computers. They interface with the operating system. They don't have to interface directly, mapping to hardware on the computer. Now we've got two different ways of producing computer generated computer code for the computer. From what we've done, we can use an interpreter. What an interpreter does is every line of code that we give it is translated one line of code and then executed. So we execute and read as we're going. With a compiler, what happens is we have to take the entire program and convert it into machine code and then sort of save it and then run that machine code after it's all been put together. And so as it says there, compiled programs run faster because you don't need to edit it to interpret one line at a time. Here's some examples of some high-level languages. C programming language is probably one of the earliest ones, C and Fortran. They've been around for a long time, and they're a little bit harder to work with. I think you'll see that here. I think we have a bit of C. Yeah, this is a C program. Sorry, I've bunched those up. But in C, we have to specify the type of each variable. With Python, that can be sort of just inferred, and the compiler takes care of that for us. So C is a lot more sort of tricky to work with. Actually, this doesn't show half of what you have to do in C to get that going. There's a lot more. Whereas Python, yeah, you can just sort of start. And away you go. Now, what have I got in this diagram here? Yeah. Okay, some different byte codes for different computers. x86, that was the original IBM desktop computer. And there's a map there of what sort of commands will be used in which way for that computer. Maybe that's interesting to you. I don't know, it just looks like a table. Yeah, we will use Python. I think maybe not in this course. You're probably using it in another course. You're doing 1201. They will be programming in Python. The other one, JavaScript. You'll use JavaScript for programming on your web pages, and PHP is also necessary for programming on web pages if you want to work with a database like an SQL database. And you can't really do much on a website without using that. All right, I'm going to stop there talking about that now and move. So that's all about what I wanted to talk to you about theory. We do have a little bit of work to do today. That is that you get to do. It's and so this is where you guys get to jump in and do something. There's an exercise in the Dropbox. So if you look at the Dropbox, now you're not actually. I'll change to look like a student, so that you can see so that I can show you what it's going to look like to you. So if I go to the Dropbox, this is what it should look like to you. There's something there about us, and there's an attachment which you'll need to open, which will explain what it is that you have to do. So you go there and open that attachment, and then you're going to submit the assignment with any comments. Come on, attachment, open up. Yes. Unavailable quick link. Oh, okay. Maybe because I'm not a student. I hope that you don't have that problem. Guys, let me know if you do. Maybe because.
So we do have, I did try and it didn't
does
come.
open?
Yeah,
It doesn't open.
No,
It does or it doesn't?
It doesn't open.
All right, so that's a problem. All right, so I'm going to stop. I will give you a link now for it. All right, so let's just go back here. I'm just going to put it on the page for you. So I'm going to edit the page. Oh, well, you don't, no, I don't need to. It's there. There's the link. So if you open from here, try this one, see if this will open for you. Okay, if that one opens, then you're good. So that's the instructions that you have to do. Binary, you need to be able to do binary, sorry? You can't?
No, so it's not coming.
It's hidden in the table of contents. Ah, that's why. Thank you. Let's go to the table of contents. Why would it be hidden? My mistake. So let's unhide it. It's not hidden. Oh, yes, it is. Make visible. It's hidden. Okay, so now you should be able to use it. All right, my apologies for that. I'm going to stop recording because this is a daft thing to be recording.